implementation is a correct implementation of this Isabel code. However, it's running on this other VM that we need for execution, and we don't know that this VM provides the semantics that we needed to assume in order to prove that this Java code was correct with respect to the Isabel code.
So okay, and with Rolang, kind of, if you have this like correct VM, like I don't know what the VM is called.
So that's the idea. So you have a correct VM, so you can rely on the semantics of the language, but even more importantly, we're not relating it to some other formal method's prover. The type checker is the prover. You get past the type checker, then your code is correct, at least with respect to the type.
That's so cool. And I wish I understood it more than like the incredible surface level that I do. It's about as surface level it could be, but it sounds very, very cool.
Yeah, well, I mean, the nice thing is that we have the ladle algorithm actually goes deeper than that. So the ladle algorithm provides this kind of mechanism for any language, assuming you have a certain kind of specification of the semantics of the language. And it turns out that the K framework people have been providing these kinds of semantics for a while now. So you can find K framework semantics for core Java, C, C++, OCaml, a bunch of languages. There was even a Solidity spec that was done in K framework. So our aim in the next few years is to extend K framework with Ladle. So you add to your language. So the Ladle algorithm takes a spec for the semantics for your language and a spec for how you want to collect your results. Do you want to collect them as lists or sets or graphs or trees or bags, what have you? And with those two inputs and sort of a kernel of a distributive law, then you can auto-generate the type system that the same kind of type system that we use for Rolang.
So you could get like the same guarantees, not the same guarantees, I guess. But
you can get similar kind. You can get tighter guarantees for Solidity, sure. JavaScript or Java or whatever.
Oh, cool! Oh, that's so cool.
Yeah, I mean, if you think about it, like even just JavaScript. Is Vlad here, by the way?
No, I don't think so.
Okay, like all of the big three. So Facebook, Google, and Microsoft have all done typed versions of JavaScript because they know that they just can't get economically viable production code out of an untyped JavaScript. And if you add up the numbers, these companies have spent hundreds of millions of dollars getting these languages to the place where they're production ready. And so that they can then deploy production code against those new languages. And this is just to get typed versions of JavaScript, right? So with the Ladle algorithm, that becomes press this button.
So cool.
Yeah, so it's kind of cool. Maybe I can talk a little bit about some brain candy research. It's related to Casper, but it's more general. In the Ladle algorithm, we need to reason about graphs. I mean, obviously, in just about anything you do, there's graph theory is like a stone's throw away from every problem in computer science, right? So it's not surprising that we run into wanting to be able to express certain things about graphs in a nice way in the Ladle algorithm. In our case, it shows up when we're providing the semantics for the possibility operator, the modal operators. So possibility, necessity, and the generalizations of those that come from the Hennessy-Milner techniques. So we've been thinking a lot about different ways to make it convenient to express things about graphs. And about 10 years ago, I had an insight that wove two branches of theoretical science together. So the two branches are, one is an old branch that goes back to like the 1960s. It was developed by William Levere and Fred Linton and a bunch of other people. Fred Linton, by the way, just passed away. So I'm happy to carry on, some aspect of his work, and the work that they did was about relating algebraic theories to monads. So it turns out that a very wide class of algebraic theories can be expressed as monads, and the other branch of research that kind of found its way into my presentation of graph theory was a seminal work by Luca Cardelli, Giorgio Gelli, and Philippa Gardner. There's an obvious representation of graphs in the process calculi. It's very, very straightforward. But because of the spatial logic operatives, you can then employ spatial logic to reason about graphs at a higher level by using formulae that pick out processes that represent graphs. And so Giorgio Gelli built a whole graph query language built around this insight. So taking those two ideas, I provided an algebraic theory for graphs. Another way to think about this is much more intuitive for programmers. So I think most programmers are very, very comfortable with recursively specified data types. Like the premier example is the list, right? So a list is either the empty list or cons an element onto a list. Right? That's it. And that has a really, really nice basic recursive definition. And that recursive definition turns out to be an algebraic theory. And so there's a monad.
1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7.
Hey, Alex, we can hear you.
Hey, we can hear you.
Hey.
I'm just in the middle of giving a quick update, and then because we were waiting for other folks. So I just took that idea and I said, all right, I can write down an algebraic theory or graphs that has this nice property. It's the idea is that graphs are just like lists are made out of lists and some operations on lists and other things. Graphs are made out of graphs and some operations on graphs and other things. And notice that this is a very different conception than the way graphs are usually presented. Usually graphs are presented as lists of nodes and edges, or lists of nodes and edges, lists of nodes in an adjacency matrix or something like that. They're not presented recursively, and that is problematic from the point of view of managing the complexity of the graphs. So I can just do a quick screen share and you can see what I'm talking about here. Oops, sorry. So here's, let's see. I'll just make this link available. I'll put it in the Chat. Let me stop the share so I can do that. Chat is where? Oh, there it is. Okay, so you can see these notes here. Someone on the ArtChain Discord has already done an implementation of the theory in Haskell and is now doing an implementation of the theory in Idris. So basically, here's the trick. So as I said, let me just.
Hello.
Hi.
Yeah. Yay! People can hear me. Excellent.
Wonderful. So here's that thing I was talking about. Here's list as a recursive algebraic theory, and then here's the same thing for graphs. So graphs as a recursive algebraic theory. Very, very straightforward. And then there are some rules for when expressions in this algebraic theory are actually well-formed graphs. So you just follow these rules and you know that the expression you've got is actually a graph. And there are also rules for membership. So you can determine when a vertex is in the graph just by following the rules. And then there are a bunch of equations on the graphics. So the syntax is more fine-grained than our interpretation of them as graphs. And so we erase those syntactical distinctions in order to get down. So the equivalence classes of these expressions actually represent graphs. And then the nice thing is now we can look at definitions of graphs. So here's a one-liner definition for the discrete graph. This one-liner recursive program, very standard, Haskell style. That gives you the discrete graph. Not a big deal, but if you compare this with the Dotty spec for the discrete graph of n nodes, the Dotty spec is many times larger. Now things start to get interesting because the chain graph, where you have links between each of the discrete vertices, is much harder to specify in Dotty, and it remains a one-liner program in this notation, in this graph theory. Now the cycle graph is even more interesting. Again, it's a one-liner program here, much more complicated in Dotty. Now the complete graph is many times more complicated, like m times more complicated or complex. And it remains a one-liner program in this notation. So basically, as the complexity of the graph is going through the roof, our specifications remain one-liner programs. They remain roughly constant. So that's the advantage of this approach. Now, it turns out, and so then I show that you can encode rewrite systems, the reduction graphs of terms in this style, and here's one for the lambda calculus. I also show that you can make the graph of the syntax of a graph, and that opens the door for reflection. And it turns out reflection is incredibly powerful, and in particular becomes super, super powerful at the point where we're interested in talking about subtypes of the type of graphs, because you can now recursively apply ladle to this language of graphs.
Hello?
And that gives you now formulae, just like the spatial logic query language for graphs. This is now a query language for graphs. And you can find the smallest domain where you pick out subtypes in this style, where you have functions from a domain into the domain of graphs, which are picking out the subtypes of graphs. And picking out subtypes using ladle. And this is the smallest domain where the two ideas coincide. So that turns out to be incredibly powerful. So basically, what we've got here is a way of representing graphs that has the very nice property that even as the complexity of the graphs goes through the roof, the complexity of the specification of the graph remains roughly constant.
But you like, do you have something that says like, okay, look, if I write a complex term in your language, that it will like be compressible into a smaller term in the language? You still have things that are complex in the.
Oh, we still have things that are complex. So basically, if the graph doesn't have nice structure, right? So if the graph is some weird sparse graph that's random, right? Then the complexity we don't get any compression using this technique if there's no internal structure, right? So if somehow you're making a graph of, you
pull a graph out of like a high entropy distribution.
Yeah, exactly. If you pull the graph out of some high entropy distribution, then we are not going to get any compression using this technique. However, the important point is that in the vast majority of sort of mainstream computer science cases, we're dealing with graphs that have highly recursive structure, and because there's been no nice data types for graphs, the complexity's been through the roof, and this changes that. And then on top of that, we get a query language for graphs. There's our query language right there, and it follows using the ladle algorithm directly from the language for graphs, which gives us this nice complexity reduction. So that's that was the sort of core insight. The implementation is relatively straightforward. And then the next step is to show how this picks out some nice things that are related to our modal operators. But that's for another story. I've gone on for too long now. Anyway, that's some research that I did.
Okay, cool. I mean, it seems cool. I wish I could do that kind of thing for any data structure. So I actually have an update that's kind of related, so I feel kind of maybe like giving it. If no one minds, I kind of was able to restate the estimate safety, consensus safety proof in terms of, rather than values of the consensus, just like propositions about the values of the consensus. So, if we had a logic to describe the value of the consensus, then I would have like the following kind of safety proof. Yeah, or they're like definitions and proof, or basically like an estimator would return true statements about the consensus. A statement about the consensus would be safe if it's true, like in the current view and in all future views. Maybe with some fault tolerance, like all future views such that there's less than some amount of faulty. Then, like that means you're safe at that fault tolerance. That proposition is safe at that fault tolerance, and if I have a safe proposition, and so do you, then as long as in the union of our views we don't have more than any of our safety thresholds, then our propositions are consistent. And then I say they're consistent because there exists a possible future where they're each true. And I think that makes sense. I'm not, but I don't know too much about the logic. But basically, like there's the proof kind of transfers over from thinking about values of the consensus to statements about the consensus, in a nice way. And the nice thing about this basically is that it lets us think about edge cases a little more easily, also because we can have, for example, no true statements that we know about. In an empty view, or we can have a view where we have like a whole bunch of options, rather than, or like it might be that block or this block. Say it's like a tie because there's no latest bets on either of them. We can express it as like or in this like kind of logic. So basically, at the end of the day, I can maybe have like a safety oracle that takes the proposition about the value of the consensus and have a way to check it. And if we can kind of like abstract that, then we might be possible, at least if the estimator has certain properties to have like the same oracle for multiple protocols, which I think is pretty cool. Another, you know, the nice thing about it is basically that it like factors the proof more nicely, just like it's more elegant proof now. And then you can think about it like you can relate it to the values of the consensus by just making propositions like, you know, the estimate is 1, the estimate is 0, or the block at this height has this hash. Yeah. So does that sound pretty reasonable? Does everyone kind of follow what I mean?
Yeah, I mean, you and I've been talking over the weekend, so I got a preview, and yeah, I understand what you're saying. If the fault context can be viewed as a dependency, then you can represent this. You can represent what you were talking about as, you know, fault context implies necessarily safety prop.
Yeah, and basically, as long as the union of reviews satisfies both your fault context, then your safe estimates are consistent.
Yeah.
Now, the question for me also is whether I could say, rather than say consistent, just say that they're both true. And I think that might be, I mean, I think that means obviously true in the union of their views. But it might not be true in the view that includes some other things. And so, you know, I mean, I guess as long as their fault tolerance, as long as the fault tolerance assumptions are violated, it'll never be false with that level of safety. Or it'll never be false at all, actually, unless there's that amount of fault tolerance.
Yeah, I'd love to figure out, you know, what's the basic language that we need in order to derive the logic.
Well, I mean, the nice thing is that we can just add things to our logic and ask about the safety of those things. You know.
Yeah. I mean, for sure. I just would love to be able to derive the logic using ladle. Just say, you know, here's the core language.
Yeah, well, for the blockchain, you could probably do that. I mean,
I think so.
So basically, you have to give basically, I'm not sure what your constraints are, but so like blocks in this like Casper friendly Ghost blockchain have like, you know, pre-block pointer, a sender, and a justification. And the pre-block pointer needs to be the fork choice rule and the justification. And then basically, so you have like, and you have this single threadedness property for honest validators.
Yeah. I mean, certainly if you start with bets and you start with, you know, agents that communicate with bets, we can absolutely derive this.
I don't know that I want to talk about properties of the agents as much as I want to talk about properties of the blockchain now. You know, I don't think the logic will be about the senders really as much as about whether blocks are going to be in the chain or whether something will be true of the chain.
Okay. Well, we can
talk about senders, you know, through inspecting the fields on the blocks.
Yeah.
Anyways, so that's basically my update. I'm sure there's more updates from, you know, Nate, Carl,
Vitalik.
Maybe
Vitalik. Yeah, can people still hear me?
Yeah.
Yep.
Yeah, so my main interesting update for the last couple of weeks is probably that we managed to get the finality gadget down from 2 message types to 1. And basically we made up for it by having consensus come in 2 epochs instead of 1 epoch. And this is nice because first of all, it simplifies the protocol and it simplifies the incentive considerations. And the other reason why it's nice is that it basically means that the efficiency goes up by basically the average amount of time you have to wait until a block gets finalized goes up by about 20%, and that's like a tiny victory. I mean, a tiny victory, but it's still a victory. So basically, the way that it works is that we replace the slashing condition that says the prepare commit consistency slashing condition with a no surround condition that basically says that two prepares can't intersect each other, and then you use two consecutive prepares to mean a prepare and a commit. The other thing that I came up with is the correct like instruction fortress rule, which basically is a fortress rule that follows along the liveness proof. So basically, here the liveness proof says that at any point you can finalize a new block by taking starting from the highest justified epoch, and so the fortress rule basically just automatically chooses the highest justified epoch, and so you know that it's going to get you somewhere. And that's probably the main update.
Cool. That's cool. Yeah. So I see some similarity in the kind of message reuse as the way that I kind of a lot of efficiency in terms of the network overhead for getting finality and my like blockchain like the friendly ghost. Basically, the one way to think about it is imagine if every consensus message was a block, and like you participated in the consensus on lots of other blocks. And basically the idea is like, with the round robin thing, you always have kind of like the 2n, or 2/3 times 2n, there are 2/3 times n times 2 like messages after the last finalized block at like a third fault tolerance. But but you kind of like have this almost all the same blocks for the next block, part of that quorum for the next block, and so on.
Right.
It's kind of a reuse of messages across rounds,
Cool.
right? So it sounds like you're using like, your message is contributing 2 rounds, right? Each message contributes to 2 rounds.
Yeah, basically that's one good way of describing what's going on.
Yeah. It seems neat. Can you describe the like no surround rule a little more?
The which round rule?
No surround.
So every preparer, or what we now call a vote, it still has a source and a target, right? So the source is supposed to be something that's already justified, and the target is something you're justifying. So the no surround rule basically says that the source and target of one epochs of one vote cannot be fully inside, in between the source and the target of another vote. So that's what we mean by saying like one vote cannot surround another vote.
So can you talk to me about like say 4 votes on like 2 blockchains, or I don't know what a surround condition?
Yeah. So let's say for example that you have one vote that does like on branch A that has source, let's say 3 and target 7, and another vote on branch B that has source 4 and target 6. That would be illegal. Now, if the second one has source 4 and target 8, that would be totally fine.
Are 3 and 4? Do 3 and 4 have to be on the same on different blockchains for that to be illegal?
No, so the slashing condition imposes does not care at all about what branch it is. It just cares about the epoch numbers.
Oh, it doesn't care at all about the branches. It only cares about the epoch numbers.
Correct.
Okay, so I can't make one that's like 4 and 6, and also make one that's 5 and 7.
No, you can do that. That's totally fine.
What am I not allowed to do?
Make one that's 4. Make one that's 3 and 7, and another that's 4 and 6.
I see. Okay. Like a complete surround. Okay. And why is that the slashing condition?
Why is that what?
The slashing condition that makes it work.
Basically, the intuitive reason for why it's banned is because your epoch source is supposed to be the highest justified epoch you know about, and so if you use one epoch as a source and then you switch to an earlier epoch, it's like you're forgetting information.
I see. Right. I see. No, I totally get it now. So if you've already made a second vote with as justified with the previous one, then like you later and you never did that to do an earlier one. This is kind of the issue. But what if they're on different forks? I mean, if you're on different forks, it may be like height 3 versus, you maybe it's legit to go on height 3 on like one fork, even though you went on height 4 on the other fork before.
Well, the idea is that you're supposed to wait until the next fork. Well, so this is in part where the correct by construction fork choice rule comes in, right?
You wait. No, sorry, go on. Yeah.
So the correct by construction fork choice rule basically says that if there is a if you made a prepare on where the source is epoch 3, then that forward say where the source is epoch 4, then that means that there is an epoch 4 on that chain which is justified, right? So then if you later switch to another chain and you do a source of or you do a vote with the source being epoch 3, then that's like never going to happen if you're honest, because it basically it means that you're switching from a superior chain to an inferior chain.
Okay, I think I got it. But is the reason? I mean, the reason why it's superior is because you saw at an earlier time.
No, the reason why it's superior in the sense of the fork choice rule is that it's what was it? Basically has a higher highest justified epoch number.
Right. So the epoch number, that's what I was saying. Yeah. The epoch, the epoch number is higher. Okay. So, if we can, is there like an attack where you like kind of skip epochs and have like a greater epoch number on some, like attack?
So let's say you do a vote that's whose source is epoch 3 on one chain, then you do another vote whose source is epoch 5 on another chain, then that is totally fine. So that's considered legitimate behavior, and this does not threaten safety or aliveness at all.
As long as epoch 3 wasn't finalized.
As long as epoch, so if epoch 3 is finalized, then that means that epoch 3 is justified and epoch 4 is justified. And if epoch 5 then becomes justified on another chain, then, so I mean, for that case, I could very quickly give the safety proof, right? So if epoch 5 is then justified on another chain, then that means that there have to be 2/3 votes, and those votes have to come from some source. If the source is 4, that means 4 is also justified, but then that means that 4 is justified on 2 different chains.
Let's say 5 and 6. Let's say 5 and 6 instead of 4 and 5 then. So you have like 3 and 4 on one chain and 5 and 6 on the other.
Okay, then we have to look at why is 5 justified, right? So 5 has to be justified. For 5 to be justified, there have to be 2/3
Right, I'm not saying 5 is justified. I'm saying 5 has the quorum.
So in order for in order for 5 to be finalized, like it would. So in order for a check, like the definition of justification is recursive as usual, right?
Okay, so you're saying the 5 has to have a previous one on the chain, and it has to have
exactly.
Okay.
Exactly.
So you have a no surround and a no double vote rule.
Yes, correct.
Okay. Okay. I hear you. Okay.
Is there a link?
Okay, cool. That's
Yay.
that works. Yeah.
Is there a link for
I feel heard. If you go to Ethereum, or if you go to the Ethereum Research discourse, then you'll find it.
Okay. If you
I'll
paste,
link it in a sec.
yeah. Link it in so the people who are watching this can.
I'm on my phone now. Can someone else do?
Yeah, Carl.
Yeah.
Oh, Nate. Anyone wants to do an update?
So I
followed the safety proof of the single message protocol in Isabel Hall. Last time with this two message for slashing conditions thing, it took me a week, but this time it took me just 1 day. Partially because the protocol is easier, partially because there was somebody called Giuliano. Giuliano contributed a much simpler proof for the previous protocol, and this time I modified that one. So I followed the safety proof in Isabel. I haven't done anything about the liveness yet. I checked the statement and I saw that it kind of requires you have to somehow ignore votes not based on justified hashes. But with that, I think it's kind of valid. So after making slides for Cancun, I'll follow the liveness proof as well.
Super cool. I would love it if you verified my safety proof too.
Oh yes. I haven't looked into your progress for a while. Yeah, maybe it's time I should do that.
Cool. I have an update as well.
Go ahead.
Okay, cool. Danny and I have been working on getting everything merged in. Kind of, this is on Vlad's CBC Casper. So kind of we've merged in like the first version of the safety oracle, or at least one of the safety oracles, and like all the cleanup stuff into the blockchain branch, and it's going great. Like Danny's doing reviews and stuff, super helpful. And kind of on my side, kind of the more recent thing is that I implemented a version of the lower bound ideal adversary, a lower bound on the ideal adversary that's kind of like a binary version of it. So this is something Vlad discussed in a previous stand-up, but pretty much it's like side effects free and converts a view with a blockchain into kind of like a view that's like binary version. It might not make much. If it's interesting, yeah, it's cool. If it's interesting, I could share screen briefly and just do like kind of a walkthrough of like the conversion step. I think it might be kind of cool.
Yeah, go for it.
Cool. Can you see my screen?
Yep.
Cool.
Yep.
Okay, so kind of we have this function get recent messages and viewables, and we're kind of looking through. We're kind of looking through a view, right, at every validator, and we're going to kind of construct model bets. So you you kind of think of like model bets are like, you know, where they're side effect free, so they just have an estimate and a sender. Okay, and so here's what we kind of say. We kind of say if we haven't seen a message from a validator, then kind of assume that they're building on the adversary estimate, and this is just we're converting to binary, right? So it's one. Or if their most recent message is conflicting with, you know, the candidate estimate, so that's the block we're asking the question about, then kind of we also say they're on the adversary estimate. Else their most recent block is on the candidate estimate, and so we're kind of good, and we can kind of say they're there. But in this case, now we kind of build viewables for this person.
Wait a second, Nate. So
yeah,
basically what you're doing is you're taking for a fork choice at a particular height, basically
yes.
with the ghost rule, you know, you start at one height and you're going to go one height at a time.
Oh,
classify everyone as either like, you know, 0 or 1 based on whether the latest message is on the block we're trying to say is safe or not.
Yep,
right?
Pretty much.
Okay, great. Go on.
And then what we do is we look through their view, or kind of the view that they've committed to in their most recent messages justification, and we kind of show them the worst case, if that makes sense. So so kind of if they haven't seen anyone for anything, we kind of simulate, because it's side effects free, we kind of just give them the worst possible case, even though this is like, totally impossible in the real world. And then that way we can kind of be sure that this is a lower bound. And we don't have to worry that we're not showing them the best stuff. But kind of what this does is it says like, if there are free messages, if there's a free message, free message being, a block that they haven't seen from some other validator that isn't on the candidate estimate, because that has the potential to change their mind, then we can kind of show them that. And then from there, and otherwise, if there are no free messages, then we can show them the candidate estimate, or in their view, we kind of say they have the candidate estimate. This is their most recent message from some other validator. And then from there, we can pretty much just run like a binary safety oracle on this, and be sure that it's a lower bound. So yeah, that's it. I can like walk through the adversary if that's interesting. It's like simplified from before.
Can you show us like the comparison of the adversaries?
Yeah, cool. So okay, so sorry, meaning like running both of them at the same time.
I'm not sure how you visualize it.
It'll take a bit to set up, so it's probably not best to do it right now. But I can talk about it for a bit. So kind of your first questions might be like, how does this compare to our clique oracle? By the way, for those of you who don't know, this is the one that kind of builds a graph out of the validators and then picks the biggest clique out of the max weight clique out of it, and says that those are all kind of locked into each other. So I did very like brief basic comparisons, and as far as I can tell, they recognize safety at the exact same time and are almost exactly as efficient as each other, which is pretty interesting.
Is that empirical or is that?
Yeah, totally. Just random measurements. And
I got it. Okay, understood.
Yeah. What's interesting is that actually the most labor-intensive part of this entire process of the entire adversary oracle is actually building checking these most recent messages and viewables in the first place. It's like most of the work that's done is done here and not actually in running the adversary, which to some degree kind of makes sense.
That's promising because that stuff is something where probably we can have like a dynamic programming kind of approach and not do as much of the work like so redundantly every round.
Yeah, there's lots of work that's redone. So, yep. Cool. Yeah, that's it for me.
Cool. I can do a super duper quick update. Basically, gave a Casper presentation at CESC. I just linked to the slides. That went well and was definitely a lot of fun. And I think I'm excited to spread the Casper love and get more and more people thinking about these kinds of problems.
Yeah.
Other than that, just moving forward on the implementation and implementing the double vote Casper friendly finality gadget scheme.
Just out of curiosity, is everyone here going to be at DevCon 3?
Yep.
Mm-hmm.
We should have like a Casper lunch or something, or Casper dinner.
That would be fun.
Yeah.
Mm-hmm. Greg, I think I can make it down if you want me to. I've been offered 2 tickets. I can bring some. Depends on if you want to record everything or just hang out.
I don't know what the policies are with respect to DevCon, but
You can't live stream anything, but they give you a press room, and you can have like private recordings in the press room.
yeah, then the co-op will pay you to go down.
Okay, cool.
One more quick update. So Vlad mentioned this thing about how we can have a generic oracle, depending a generic oracle for some consensus that has an estimator with some properties. And so kind of the one other interesting thing that I did was like refactor both the adversary oracle and the clique oracle, the other oracle, kind of are totally agnostic to this point to the underlying data structure if the estimator function has like this majority locked in deal. And so kind of it's like all very abstract, and you just kind of have to implement this interface that's just like, our 2 estimates conflicting, and if you implement that, then you can kind of use this for binary or for blockchain or for like the rewrite proof thing. I think that Vlad talks about sometimes. So that's kind of cool too.
Yeah, it seems like the domain is all abstracted away in the estimator.
Yep.
And basically, like right now, we're talking about kind of comparing latest messages, seeing whether they conflict or not with the estimate that we're trying to say is safe.
Yeah.
And if you can always say that, like, okay, out of all the latest messages, like, do you agree or not? And you have the property that if like a majority see, a majority agree, then majority all agree, or I guess.
Yeah.
There's like yeah. Well, I mean, it's like
that's the circularity. Yeah.
Mm-hmm.
Yeah. Cool. Any other updates?
I'm starting to do some work with Nate on the repo, focusing on code review, cleanup, etc., to get familiar, and then kind of moving from there. With the goal to make this more, better ready for like public digestion and maybe extensibility. Hopefully at the end of this month.
Yay.
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 Yay. Woo. All right. So, anyone have anything they want to talk about real quick before our meeting's up?
I realized that my screen share was off while I was going through the graph. So just for the a camera for the people who might watch later, I'm just going to quickly screen share and let people see what I was talking about very briefly here. So here's the idea that list is a recursive data structure. Here's the same kind of data structure for graphs. Here's how to determine that graphs are well formed. Here's how to determine that a vertex is a member of the graph. Here's how to erase syntactic distinctions so the graphs are really equivalence classes of expressions. Here are standard examples of graphs.
Lucius.
Yes.
So very intuitive trees can be represented as terms because you follow a branch, you follow a branch, you follow a branch, and when you choose any different branches, you end up on a different node.
Mm-hmm.
But when the nodes are shared, like, okay, when the file system contains symbolic links, the structure gets more interesting with cycles.
Much more interesting with cycles, exactly.
Yeah, and I'm wondering about the approach you take about these cycles.
Yeah, the first thing is that links are never directly between vertices. Links are always between references to vertices.
Oh, references.
Yes. So that's why the type is parametric into two things: a set of variables which allow you to build references, or a collection of variables, and a collection of vertices.
Collection of V's, what?
So V's are the vertices. So
okay.
X's are variables, V's are vertices.
Okay.
Gamma is your dependency. Gamma is your dependency list.
Okay. Okay. So it's somehow. I see.
Yeah, it's much more. It's more subtle than it at first it appears.
Yeah. Okay. So there's a layer of indirection using variables. So that's why you can represent structure.
Exactly. That's exactly, and that's what allows me to do not only cyclic graphs, but I reiterate the same construction at the level of not just links, but graph references themselves. So there's a whole section here where what you do is you bifurcate the set of variables into variables for vertices and variable for graphs. And then there's a cut rule, which allows you to build recursive graphs within the language itself. which is quite nice, right? So it's like I completely skirt the whole subgraph isomorphism problem. Right? I completely avoid all of that complexity, and yet I still get, graphs inside graphs.
Can I stay a little bit more at the cut? Okay, well, I can follow the link and
Yeah,
I
you
can
can
do.
follow. You can follow the link exactly. This is just because we're just about out of time, and then the main thing is because I have variables and vertices, I can do reflective tricks, right? So I can make consider the domain D, which is recursively defined as the graph domain, in which you sum the variables with the domain D and the vertices with the domain D. So now elements of the domain D can be used as variables, or they can be used as vertices. So we now have reflective notations. You can turn a graph into a variable, or you can turn it into a vertex, which is incredibly useful. And then here's the little graph query language or graph data type language. So it allows you to describe types of graphs of which the elements of the domain can be matched, and there's a clear matching algorithm. So I just wanted to get that on camera. So the link is in the thing, and then what I said before. If you look over the examples, discrete graph is one-liner, chain graph is one-liner, cycle graph is one-liner, complete graph is a one-liner. Here's the one-liner right here. So as the complexity of the graph goes up, the specification for the graph remains roughly constant.
If there's still a lot of structure.
If there's a lot of that's right. If you have high entropy distributions, all bets are off. But that's the case everywhere, right? Where computing gives you compression on stuff that has nice computable structure. If there's no nice computable structure, there's no compression.
Yeah. All
right, cool, guys.
That's comforting. All right.
Vlad and Greg, are we going to hop on real quick?
Yes, right after this call. Do we want to? We can use my Zoom room.
Okay. Can you put the link?
Yeah.
Let me end the broadcast first. Are we done, guys?
Yeah, you can end the broadcast.
Anyways, yeah, bye everyone.
All right, see you, everyone.
Ciao.
Bye, guys.